Okay, now we will continue to talk about the VAR model. So here is an example of the economic model. So what we can observe is that firms set free prices on the basis of current overall price levels, and the government sets administered prices G on the basis of current overall price level. The overall price level is the weighted sum of free and administered prices. So we can structure this kind of econometric model. So for the current administered price, it is affected by previous administered price, and also it is affected by current and previous free price. Because when you set regulations, you need to base that decision on the previous free price and also the previous regulations. And for the free price, it is affected by current and previous regulations or the administered price, but also it is affected by its previous free price. So we have this kind of structure. If we combine these two together, we can form this kind of representation. But how did we achieve that? We need to shift all the current term into the left hand side of the equation. So shift this one to here, and also shift this one, the current administered price, to the left hand side. Then we get all the current term, and then we summarize the variables as a PT, and we summarize all the coefficient as A. And then we on the right hand side, we only have the lag terms, and then we combine all the lag terms to be pt minus 1, and then we summarize all the coefficient of the pt minus 1 as B. And then we also combine the error term as this one. Then we will find that for the A it can be represented like this, and for the B it's like this. For the for the PT and PT minus 1, we will combine the administered price and the free price into one vector. And then if we denote this one into the lag terms, then we can represent it into this way. So the lag function of the PT equals the lag function of the error term, where the CL is a function of the lag operations, and DL is, in this case, is identity matrix, but in some other case it can have a kind of structure. But we will meet some big problems. First, we cannot estimate the structural system directly. Instead of this one, what we can estimate is a reduced form. Because if we have the A here and A at the left hand side but the B at the right hand side, it is impossible to estimate because you will have the endogenous problems. If you want to know more about endogeneity issues, you can refer to other slide. But here, if you estimate that, the estimation has a bias. So you need to move the A matrix to the right hand side. In this way, you can make a kind of accurate estimation of all the coefficient in this equation. Then the estimation issue 1 is that which estimation method should we choose? we can use the OLS because all variables are the same on the right hand side for each equation, right? As long as we use the same number of legs for each equation, then it is good to use the OLS. But if not, it will be more efficient to use the seemingly unrelated regressions. SUR is a very similar model as the VAR, but they can deal with a variable with an equation with different number of legs. Oh, and one assumption is that if we have a multivariate regression, if on the right hand side we have the same kind of the independent variables, then you will gain nothing from the seemingly unrelated regression. So you can use the OLS. But if the variables in each equation is different, then you will get more efficiency by using the seemingly unrelated regressions. And another estimation issue is, should the variables in the VAR be stationary? Actually, it is yes or no. Non-stationary variables might lead to spurious results, but Chris Sims argues that by differencing or detrending, a lot of information is lost, and that we are interested in the interrelationships between the variables, not the coefficients themselves. Therefore, we can use the non-stationary variable if the only thing that interests us is to get an impulse response to the shocks. But if we really want to get an accurate coefficient, then we may need to use all the stationary variables. The estimation issue 3 is, how many legs should we use? If we use more legs, it will improve the fit of the model to the empirical data, but it will also reduce the degrees of freedom and increase the likelihood of overfitting. So sometimes if we add just one leg, it will exponentially increase the number of variables that we need to estimate. For the overfitting, if a stationary process look like this, but this does not imply that you improve the model by increasing the number of legs. A big problem is noisy data. By increasing the number of explanatory variable, you may be explaining noise, not the underlying data of interest. So sometimes we will increase a lot of variables just trying to explain the shocks. Actually, shock should not be explained, but you may explain that part, and you will find some variable is really important in explaining the shocks, but that it has no meaning in the VAR model. So we may incur the overfitting problems in the VAR model because we need to incorporate a lot of variables in each equation. So 2 ways to run these problems. First, the economic theory might suggest appropriate lag lengths. So for example, the impulse response of the inflation to the monetary policy shock is approximately 6 months. Therefore, we do not need to include a lot of lag terms if we use quarterly data. Only 2 or 3 lags should be enough. Another way is to use lag length selection criteria. It will help you to make the trade-off between the parsimony against fit. But think about the result. Do you really believe in them? So that one is using the econometric way or statistic way to calculate the lag number. But do you believe in them? And do they suggest you should seasonally adjust it? They cannot tell you whether there's seasonality in the variable, although you still have some tests to test the seasonality. But the Lagrange selection criteria cannot tell you anything about the seasonality. And the second big problem of the estimation should be we can move easily from the structural model to the reduced form, but not the other way. In this example, we estimate 7 parameters, but the structural model has 8. Therefore, there are an infinite number of ways of moving from reduced form to the unobserved structural model. What does that mean? If we want to have a structural model, we would like to impose some structure among the interaction of all the endogenous variables. Otherwise, we will have several possible impulse response to just one shock. In that way, we cannot identify which impulse response should be the appropriate one. Therefore, we need to impose some kind of structures. So, 8 unknowns and 7 estimates. In our examples, we need to make one of the unknowns known. For example, we need to set the value of at least one coefficient, make an identifying restrictions. So if we make one identifying restriction, the system is just identified. If we make more than one, it is over-identified. We can then test restrictions. So let's go back to the original problem. It is here. So how many variables we need to estimate? 1, 2, 3, 4, 5, 6, 7, 8. We have the 8. But the maximum number that we can estimate is 7. So if you want to know more about the estimation, you should refer to the econometric class. But yeah, the maximum number that you can estimate is 7. If you need to estimate the 8 variables, then you will incur some problems. You cannot fully identify. So to summarize, the most the easiest VAR model, the unrestricted VAR models, which means you do not impose any structure for the coefficient, but for the structural VAR, you will impose some kind of restriction to the coefficient. To summarize, we estimate an unrestricted or reduced form VAR. That is something like this. We call this kind of form with the A matrix on the right hand side as a reduced form. The unrestricted, we estimate an unrestricted VAR. By imposing suitable theoretical restrictions, we can recover the restricted or structural VAR. So, if we can find some restriction between of the coefficient from the theoretical paper, we can impose that, and then we can figure out a way to estimate all the other variables. And the unrestricted VAR is a statistical description of the data. The structural VAR adds some economics because we need to make some restrictions based on the economic models, and then we can also define some of the statistic variables with some of the economic meaning. For example, we can identify the shocks in the inflation as a demand shock, then we can impose. In that way, we will know more about the economics rather than the econometrics. And the unrestricted VAR compatible with a lot of series. It produces good short-term forecast. It will tell you whether it will test whether a theoretical model is good or bad. If a theoretical model can have a good forecast, then we can say it is a good one. The structural VAR tied to a particular theory provides a better interpretation of forecast. So if we get the forecast, if we have the impulse response with the structural VAR, we can interpret it in an economic environment or economic background. And for the long-term forecast, it is a combination of both. For the structural VAR, is it better for a central bank? And that is hard to say. Actually, there's a lot of economists only focus on the reduced form VAR, and they still get a very good result or publish very good papers. So in next part, I will talk about identification and why we actually need this kind of identification to provide some economic meanings. So that's all for this part. Thank you for listening.